Hello, this is the solution video for calculus homework assignment number 15. So, for these 6 questions, we are going to be determining the zeros of these functions. So we'll start with question 10. So our function is f of x equals negative 2x times the square of 3x plus 2 times 3 minus 2x. For this function, in order to find the zeros, all I need to do is set it up as a factored polynomial. So I have 0, setting my function equal to 0, equals negative 2x times 3x plus 2. And I'm actually going to go ahead and just write this as the square, so the multiplication of these two identical binomials, times 3 minus 2x. And then set each factor equal to 0. So if I set negative 2x equal to 0, then I would just say that x equals 0. There's one of my zeros. If I set 3x plus 2 equal to 0, then I would find that 3x equals negative 2 and x equals negative 2/3. And I actually can skip a little bit of math here. This being an identical binomial or an identical root would just mean that I have a double 0 at x equals negative 2/3. Then for the last term, I have 3 minus 2x equal to 0. So negative 2x equals negative 3, and x equals a positive 3/2. So that is all there is to finding the roots for question number 10. Number 11 is a little more complex. I have the function g in terms of t is equal to t plus 5 over t minus 1 minus 5 over t minus 7. So in order to figure out what makes this function equal to 0, I will actually need to do a little bit of combining for these two fractions. So I'm going to go ahead and rewrite this as 0 equals, actually I will rewrite it to the left so that I can write straight down. 0 equals t plus 5 over t minus 1 minus 5 over t minus 7. So the first thing I'm going to do is going to combine these two fractions, and in order to do that I need a common denominator. So I'll actually multiply the left by, see if I can write this over here, t minus 7 over t minus 7, so that I can get the same common denominator, and I'll multiply the fraction on the right by t minus 1 over t minus 1. And so what this gives me is t plus 5 times t minus 7 over t minus 1 times t minus 7 minus 5 times t minus 1 over t minus 1. And I'm writing it in this order to make it apparent that we have the same denominator, times t minus 7. So I'm going to go ahead and combine these. I'm going to go to the right here so that I don't run out of room. And when I do that, I will end up with t plus 5 times t minus 7 minus 5 times t minus 1 all over t minus 1 times t minus 7. Now, in order for this function to be 0, I don't care about my asymptotes, which would come from my denominator being 0. I only care about when the numerator is equal to 0. So really I can simplify right now and just look at when the numerator is 0. So that's just when t plus 5 times t minus 7 minus 5 times t minus 1 is equal to 0. So I'm going to go ahead and FOIL out this. So I end up with t squared minus 7t plus 5t minus 35. And I'm also going to distribute the 5 at this part. So I have minus 5t plus 5. And so a little bit of simplification here. I can get rid of these two as they cancel each other out. And then I can also add the negative 35 and 5. So I end up with the quadratic equation t squared minus 7t minus 30 is equal to 0. So I can just go ahead and factor this one as I did in the first question. So when I factor this, I can do test and figure out that this would factor to t minus 10 times t plus 3. Therefore, I can set each of these equal to 0, so I would have t minus 10 equals 0. So 1, 0 is that t equals 10. And another 0 would be when I set t plus 3 equal to 0, so that is t equals negative 3. So that's it for number 11. Now number 12 is actually not as difficult as it looks. I'm going to change color slightly so that we can see here because I'm a little short on room. So number 12, you have the expression 4u cubed. So this is p. So p of u is equal to 4u cubed ln of u minus 5u squared ln of u minus 6u ln of u. So again, to find the zeros, I'm actually just going to need to factor this. So setting p of u equal to 0, I'm going to factor out a u and an ln of u because every single term involves those two things. So if I factor out a u and ln of u, what's left over is 4 and then 2u's, so that's u squared, minus 5, and now 1u is remaining in the second term. And then in the last term, all that remains is a 6. So I have now a quadratic that I can factor. So if I guess and check for this quadratic, I will actually find that my first term should be 4u, my second will be a u, therefore, and I should actually end up with this first binomial being 4u plus 3 and u minus 2. And now I just set each of these equal to 0 in order to find all of the zeros. So one obvious one here is that u equals 0. Second, when I set ln of u equal to 0, well, that just implies e to what power gives me 0? Well, the only thing that can give me, e to the 0 power gives me what? And so the only thing that would give me is 1. So that's my second 0. Then I have 4u plus 3 equal to 0. So that would be 4u equals negative 3. Therefore, this 0 is negative 3/4. And for my final 0, u minus 2 equals 0. Therefore, u equals 2 is my final 0. So this, again, is just factoring like we've seen in some tests and quizzes before. Now to question 13. So question 13, so this is function r of x equals ln of 2x plus 1 minus ln of x minus 2 minus 1. In order to solve this one, I actually need to know the properties of logarithms. So if I have two logarithms of the same base, so these are both ln, so they have a base e, then I can actually put those together if they are adding or subtracting. And so the property there would be, if I have one logarithm subtracting from another of the same base, I can rewrite this as the quotient of these two arguments. So I would write this as ln of 2x plus 1 over x minus 2. So I just combine these two terms using properties of logarithms. And then minus 1. So I'm still trying to solve for when this is equal to 0. So I've set my r of x equal to 0. Now I need to go ahead and solve for some values of x that give me this 0. So I'm going to go ahead and move my 1 over to the other side. And my natural log remains on the right side, as is. And my next step will actually be to get rid of that natural log using an anti-log, or in this case I'm going to exponentiate both sides. So I would have on the left side e to the 1, and on the right side, so what I'm doing here is I'm just doing e raised to that power. And so on the right-hand side, my natural log goes away, and I'm left with 2x plus 1 over x minus 2. So now in order to get to the next step, I'm going to go ahead and try to solve for x. So I'm going to multiply both sides by x minus 2. And what that does for me is I end up with e, I'm just going to write e instead of e to the 1, times x minus 2 equals 2x plus 1. So now all I need to do is distribute my e. So I have e, I'm going to write it as x times e minus 2e equals 2x plus 1. Now I want to get all of my x terms on one side so that I can factor them out. So I'll go ahead and just subtract 2x. So I'll have x times e minus 2x. And when I move this over and subtract the 2x, I'm going to go ahead and add 2e to the other side. So again, what I'm doing here is I am subtracting 2x from the right side, and I am adding 2e to the right side, which gets rid of it. Or I'm technically doing this on both sides. So then I have 1 plus 2e on the right-hand side. Then I will factor out my x. So I have x times e minus 2 equals 1 plus 2e. And now I can divide both sides by e minus 2, leaving me with just the single root of x equals 1 plus 2e over e minus 2. So, moving on to question 14. So question 14 involves now an exponentiated function. So we have v of t equals e to the t squared minus 1 minus 5. So setting this equal to 0, I would have e to the t squared minus 1 minus 5. And I'm going to go ahead and move that 5 over to the other side. So I have 5 equals e raised to the t squared minus 1. Now I need to get rid of this exponential, so I'm going to go ahead and take the natural log of both sides. So I would have natural log of 5 on the left-hand side, and on the right-hand side my ln of e goes away, and I'm left with just t squared minus 1. So now it just becomes a simple thing of finding a value for t, or solving for t. So I'm going to go ahead and add 1 to both sides, so I have ln of 5 plus 1 equals t squared. I don't like the t, or the variable I'm solving for, on the right-hand side, so I'm going to go ahead and rearrange this. So t squared equals ln of 5 plus 1. Then I'm going to simply square root both sides. So my root is technically a double root here, where I'm going to have the plus or minus of square root of ln of 5 plus 1. So it doesn't look very pretty to have a natural log within a square root, but it is perfectly acceptable because natural log of 5 is just some number. Finally, for number 15, we have the function L of t, and that is equal to 3 raised to the t squared minus 1 minus 5. So again, I'm going to make my function equal to 0, so 3 raised to the t squared minus 1 minus 5 is equal to 0. I'm going to move my 5 over, because now I'm trying to solve for t. So that's 5 equals 3 raised to the t squared minus 1. And now in order to get this base 3 out of the way, I'm going to take the natural log of both sides again. And so what does that do for us? So I have ln of 5 equals ln of 3 raised to the t squared minus 1. So one of the properties of logarithms is that if I have an argument for a log that has a power, I can actually take that power and multiply my natural log by it. So this ends up being able to be rewritten as t squared minus 1 times ln of 3. So now it just becomes a process of solving for t squared. So I'm going to divide both sides by ln of 3. So I have ln of 5 divided by ln of 3 is equal to t squared minus 1. And so I'm going to go ahead and move my t squared over to the other side. So I have t squared, and I'm going to add 1 at the same time, if that's all right. So I have t squared is equal to ln of 5 over ln of 3 plus 1. So I've added 1 to both sides, and then I've moved my t squared to the left side. So now it is just simply taking a square root of both sides. So t would be equal to plus or minus the square root of ln of 5 over ln of 3 plus 1. So again, this doesn't look very pretty, but if you wanted to go ahead and use a calculator to find these two values, you can do that.